Welcome back to ECE 441A, 541A. I'm impressed that I have any attendance in the classroom. Maybe I should, wow. There, is that a little bit better? A few announcements before we get started. Quiz number 1 is due Monday, but there is no class on Monday. I think you probably know that. No, you still turn it in. Homework number 1 is due on the 11th, which I believe is Sunday evening. I did post some review material for exam number 1. That's now on the D2L website in its own little module. And I'm suggesting I make a change to my Thursday office hours. I'm having a lot of conflicts at that time from 3:30 to 4:30, so I thought since you guys like this 9 o'clock time, I would slide it to 9 o'clock on Thursday. That actually might work for the seniors that are in the capstone that had a conflict already with 3:30 on Thursday. If there aren't any objections, I'm going to make that change for the rest of the semester. Today what I want to do is review the approach to finding the equations of motion for a dynamical system in general, and then I will quickly recap what we've done for the 3-mass system and maybe try to show how this relationship between the positions or the velocities when we're finding these forces actually determines on how we've labeled those, in what directions. And last time I consistently made those directions all go to the right. If you started shuffling those, then you're not necessarily going to have this immediate x1 minus x4, etc. Then we'll discuss placing those dynamic equations into a state space representation. Because the state space representation is not unique. You could label those states many different ways, or you could label those masses in many different directions and or with different labels, and you might have exactly the same system but different representations, but they would still be consistent, those representations. You would still get similar results. It's just your x1 might not be the same as your neighbor's x1. And then we'll talk about deriving a transfer function from a classical block diagram, and that's going to lead us to our second cheer. Since it's Friday and we have to get ready for games, we'll have cheer number 2 at the end. Here's a quick outline of how you can derive equations for a mechanical system. First, you want to know what system you're playing with or trying to analyze. Sketching that helps. Then you identify the variables. You can then, for each of the different positions of interest, sketch the free body diagram. And once you have that and the forces identified, you can start developing these relationships between the coefficients and the positions and the velocities. And finally, you can write those equilibrium equations, substituting in those force expressions to derive the equations of motion. Here's our 3-mass system. I hope that's the same system that we had last time. I believe it is. I don't see a U sub 2, so we don't have U2 or we don't have U-tube anywhere in this particular system. We do have 2 external forces, U sub 1 and U sub 3, and those are actually going in different directions, and one is actually moving in a direction that opposes or sort of is against the direction that we've assigned for mass 3's positive direction. And what I want to do now is maybe later I will say, what if we had assigned this as, instead of displacement 4 going to the right, maybe we said let's call our displacement for whatever reason W so that it's distinct from Z sub 4, and suppose we said that's W sub 4 going to the left, and how would that impact our equations? But this is the system that we need to memorize so that we can move forward. If we look at free body diagram number 1, again, I'm scrolling through this assuming that you can look at these notes afterwards and don't have to frantically be writing, because you already have this, we've already derived it, but this now allows us in the free body diagram to virtually move each mass one at a time in the direction that we've labeled positive for that mass's position and velocity. And once we do that, what particular forces now become active once we've virtually tried to move that in the positive Z1 direction? Then you'll have the spring forces opposing that, you'll have the dash pot force, you'll have the inertial force, and then the reference input will be in whatever direction it was applied. And you just live with that particular direction. In this case, U sub 1 was opposite all of the other forces in that system. Now, the only thing that I can say differently from last time is suppose now that instead of Z sub 4, we actually made it W4. It would have been, let's say, Z sub 4 going the other direction, but I wanted to make sure it's clear that I'm not mixing my W's and Z's. Let's just say the position we assigned for that other point is W4. And what is F sub 1, or the force due to spring K sub 2 in free body diagram number 1? What is its expression in terms of Z1 and W4 and K sub 2? I'll do the hard part. The spring constant. Now the force due to the spring is K times displacement. Now we need to determine what would actually happen relative to each end of that particular spring. And it's connected relative to position 1 and position W4. And one way that I like to do it is actually sometimes just fix one of those positions and move the other one and see if the sign gives me the direction that I need. For example, if I fixed omega 1 virtually, let me just say I fix it, and now I move the mass Z1 in the Z1 direction, do I obtain a force going to the left that's proportional to K sub 2 times what? Times that particular position that I've moved, which was Z1. Now, if I fix Z1 and I say I want a force going to the left for F sub K sub 2, and that's going to be associated with spring K sub 2, what do I need to do with the right-hand side of that spring? Is it minus W4? It's plus W4, because now if I move it in the positive W4 direction, that will give me a force going to the left. And so now in this case, I have not Z1 minus Z4, I would have Z1 plus omega sub 4. But that should have been obvious since Z4 is just the negative of W4. But if you hadn't already looked at Z sub 4 and you just labeled it W4, wherever you had in this free body diagram F sub 1 K sub 2, you would replace it with K sub 2 times Z sub 1 plus W4. Is that clear? Does that help explain this relationship between the positions or velocity variables and those coefficients, weighting coefficients? And then we end up with this second order coupled differential equation for, or resulting from, free body diagram number 1, or for mass number 1. Free body diagram number 2, and remind me in the back if I don't get it up high enough, but here's free body diagram number 2. We only had one external spring or dashpot attached to that mass, and we have its inertia associated with it, and those are the two forces resulting in that second order differential equation. Free body number, or for mass number 3, again we need to just identify what is the result of displacing that in the positive z sub 3 direction. We have our three forces, including the inertial force, and we have the externally applied input, u sub 3, that's moving in the same direction as those other forces due to spring 3, dashpot 3, and the mass m sub 3. And finally, for the massless point between, I think, mass 2 and mass 1, we identified that and labeled that as point number 4. It was massless. If you were confused, you could put a mass there and say, oh, this is mass 4, and then just give it a 0 weight. If you said, well, I know how to do this if it was a mass, okay, well, do it as if it was a mass and just give it 0 mass, and then you'll end up with the same equation. You have the two forces when you displace that point in the positive z4 direction. To give you those forces in the left direction relative to those positions and velocities, you need to then write those as b sub 2 times the quantity z sub 4 prime minus z sub 2 prime plus k sub 2 z sub 4 minus z sub 1. That we've already worked through, and I'm hoping that is just there as sort of thing that we can refer back to when we now want to put that into a state space representation. Again, this state space representation is not unique, and sometimes it's nice or maybe essential to understand what you're playing with or working with. And in this case, what are we working with means what's the size of our state vector? What is little n? What is Nevada? How tall is that vector? How many state variables or coordinates do we have in that x vector resulting from this particular system? And last time we sort of gave this strategy. We look at all of our coupled differential equations, say, okay, what's the highest power derivative of each of those variables? Z sub 1 is differentiated twice, so we'll need two state variables for that. Z sub 2 is differentiated twice, we'll need 2 for that. Going to run out of fingers. We now have Z sub 3, 2 for that. I may have to take off my shoes, get to my toes. Hopefully not. And then what else do we have? Just 1 for Z sub 4. So we have 7 state variables that we need to make up our state vector. Our system order is 7. If somebody said, oh, you have a 7th order dynamic system, that's what your denominator would be. If in a transfer function it would have an s to the 7th, and you would have 7 poles, or 7 in this time domain description. You have a system matrix A. If you found the eigenvalues of A, those are the poles of your system, and that will give you the dynamic behavior of your open loop system. To do then is for this standard form, x prime equal ax plus bu, y of t equaling cx of t plus d u of t, we now need to populate these matrices, A, B, C, and D, with the appropriate coefficients, resulting from the equations that we just derived for that 3-mass system. And we just said that x our state vector has 7 coordinates, which means that it's this tall, thin vector, 7 rows tall, 1 column wide. What's our input vector? U of t. That now contains all of our inputs that have been identified that are being applied to that system. How many do we have? 2. Even though they're labeled U sub 1 and U sub 3, we just have 2. This is now a vector that is TWO tall. It's not TOO tall. It's TWO 2 tall and 1 column wide. And well, we'll talk about the output maybe in just a minute. Now what we want to do is actually assign the coordinates to that state vector. What are our 7 entries in that state vector? And this is where the non-uniqueness can enter. Here I'm going to say, let's just let x1, the first coordinate, be the position of mass 1. And in our equations, we were calling that z sub 1. And let me make z sub 2 equal the derivative of z sub 1. And now I think you can start to see where the non-uniqueness would be. I could have made z sub 2 equal to z sub... Thank you. Must be too early. X sub 2. X sub 2 is equal to z sub 1 prime. Just making sure you're awake. Oh, of course. I'm ready for a nap. I don't know about you. But that's fine. All right, we'll have, no. What's x sub 3? X sub 3 is whatever we want that's left over, but let's go ahead and sort of go in the logical, let's call that z sub 2. Then x sub 4, let's say that's z sub 2 prime, or the velocity of mass 2. X sub 5, let's say that's the position of mass 3, z sub 3. X sub 6 of t is now the velocity of mass 3. And finally, let's say x sub 7 is the position of point 4 that was between mass 1 and mass 2, in between spring 2 and one of the dash pots, whichever dash pot that was, dash pot 2. But somebody could have said, oh, I want x1 to be the position of that point, z sub 4. Do you see the non-uniqueness that would arise? That's okay. You just need to keep track and be consistent once you've assigned your state variables. This might be a more logical or intuitive assignment, starting with sort of mass 1, mass 2, mass 3, and then that last point, point 4. Now what we haven't done yet is identified any outputs in this system, any y's. And depending on what you're working on, that may already be given, or maybe you now have to design a system and you have to specify what sensors you're using or what variables you're now calling outputs. In this case, let me just say for this example, let's select positions. Of masses In this case, we have more than one mass, but in general, if we just had one mass, maybe we would just have one output. Here we are actually going to have output for every mass, and we have three masses. We are now suggesting that for this example, let's just say that we now have our output vector y is 3 coordinates tall, and we're now going to make y be a function of our x's and input, and we now have said, oh, x1 is mass 1, so let's just say that y1 is x1. y2, let's say, is the position of mass 2, and what is the position of mass 2 in terms of our states? 2, but we've defined that to be x sub 3, so this is now going to be x sub 3 of t. And our third mass, z sub 3, was coordinate 5 in our state vector. Our third output then will be x sub 5, which says that our output is now 3 by 1. Now that we have all of those vectors defined in terms of their sizes, x is 7 by 1, u is 2 by 1, and y is 3 by 1, we can start to build our state space representation. There's x prime, and it is 7 tall and 1 wide. How big is A as a matrix? You know it has to be compatible with the left-hand side. The left-hand side ended up with 7 rows, so you know that A has to have 7 rows. And what did we say about the shape? It's square. And you could say, well, it also has to be compatible with the state vector, and which means that when we multiply A times x, it better be compatible, and so we need 7 columns to match the 7 rows in x. And we can do the same thing with our input matrix and our input vector. How wide is B? How many columns does B have? It has to be compatible with our input U, which was 2 rows tall. And how tall is B? It has to be such that we can add it to a 7 by 1 vector. It has to have 7 rows. So B is now a 7 by 2 matrix, our input matrix. Right now, how many entries do we have? We have 49 coefficients in the A matrix. And how many coefficients do we have in the B matrix? 7 in each column, 14. So we now have 49 plus 14. 63. So now we have 63 entries in this description of our system. A lot of those might be zeros, but we have to identify where those are at. What about the output equation? this is our C and D. Our output matrix C, and D is our direct feed-through matrix. And once we have Y, X, and U defined dimensionally, or how big they are, then C and D are determined or fixed. Y, the output vector Y, not WHY. Hopefully it's clear why those matrices are fixed, C and D. The output vector Y is 3 tall and 1 wide. X again is 7 tall and 1 wide, and U is 2 tall and 1 wide. What's the dimension of C? And we do row times column. 3 to be consistent with the rows in our output vector, and number of columns 7 to be compatible or consistent with our state vector X. C is 3 by 7. Pardon? And D, 3 by 2. And you may not be able to buy these off the shelf at Home Depot if you go and ask for a D matrix, a 3 by 2, or they usually sell 2 by 4s and 2 by 6s, 2 by 8s. Sorry. Now we need to build these entries. We have 49 entries in A to try to find. It's not that bad. We need to find what is the first derivative of x1 equal to in terms of x1, x2, x3, up to x7, and u1, u2. Yes? I don't have a program to solve this. The question was, I thought you had a program to solve this. No, you actually have to put the numbers into the program to make it work. If you have a program that deals with A, B, C, and D, then that's okay, but you have to build the A, B, C, and D to begin with. We have to populate these A, B's, and C's in terms of their matrix representation. This is now the first derivative of x1, but that's just the first derivative of z1, which was z1 prime, and can we write z1 prime in terms of x's and u's? Yes. Pardon? This is just x sub 2. Which means if we have this A matrix and the B matrix, what have we now determined? What piece or pieces of A and B have we now found from that equation at the top of the screen? Have we found the columns? Have we found the diagonal? Have we found a row? Or are we still lost? We now have the top row, because this top row is going to give us x1 prime, which is the leftmost entry in the top element of the x prime vector. We now found x1 prime. What we now have identified are the entries in the top row of A and B. How do we populate that? We have 7 columns to fill in the top row. We want that top row of A to look like. We want it, when multiplied by x, to equal x sub 2. So we want nothing to do with x1. So we weight that with a 0. We definitely want x2, and that's all we want. We just need 1 times x sub 2, and everything else becomes 0. So there's 3, 4, 5, 6, and 7. And that's the top row of A. What's the top row of B? What U's do we have over here in this expression? We don't have any. So B is in the top row 0. 0, 0. More interesting structure now starts to enter in the second row of A, because the second row of A is supposed to be giving rise to the expression for x sub 2 prime. X sub 2 prime is the acceleration of mass 1. And that, if I keep track, if I just write it down, that was K1 M1 Z1 minus B1 over M1 Z sub 1 prime minus K sub 2 over M1 Z sub 1 plus, all of these are still on the right, K sub 2 over M1 Z sub 4 minus K sub 3 over M sub 1 Z sub 1 plus K sub 3 over M1 Z sub 3 plus 1 over M1 U sub 1. And that's all from that second order differential equation, from the free body diagram for mass 1, and I've simply multiplied it out, distributed all of the terms so that I now have each one individually expressed, which now allows me to combine like coefficients for the like factors of z1, z2, etc. Let me collect all of the coefficients that scale z1. I now have minus k1 over m1. That's that one. I have minus k sub 2 over m1. And did I miss? No, minus k sub 3 over m1 right there, and that's now z1 of t. Minus b1 over m1 z1 prime of t plus k2 over m1 z sub 4. Let me do the z sub 3 first. Let me go ahead and find that. So that's k sub 3 plus k sub 2 over m1 z sub 4 plus 1 over m1 u sub 1. But I don't want z's, do I? I need to replace those with their associated x's. This z1 was just x1 of t. z1 prime, that was x2. z3, the position of mass 3 was z5. Just making sure that you're awake. Thank you. x5. Sounds like cars or something. We have an x5. Sorry. z4. This was x sub 7. Glad I have you guys to help. And then u1 is just u1 of t. Which means we are now in a position to start putting these into the second row of our A matrix and the second row of our B matrix. This mess, 3 terms, is the A21 coefficient in my A matrix. That's in the second row, first column, because it weights x1 and it needs to be in the second row. For that, I would calculate what that coefficient is, and that's now in the 2-1 entry of my A matrix. What's this coefficient. How can I label this one? Where does it appear in the A matrix? Second row, second column. The one scaling x5 is now A, second column, I'm sorry, second row, fifth column. It's A25. The next term is in the second row in the seventh column. What's the 1 over M1? Where does that belong? That's in the B matrix. And it's weighting U sub 1. It's going to be in the first column, and it's in the second row because it's in the x2 prime equation. This is now B sub 2, 1. Which says now that A, we have it built up a little bit better, and so with B. We already had this. That was the top row of A and B. And now we have, bless you, the 7 entries or columns. We now have A21, A22, A25, and A27. And what do we have in the missing zeros? And there's now the second row of A. What about the second row of B? We didn't have any U2, and there's B. I'm sorry, the second component of U, which we actually called U sub 3. A question, or are we stretching? Stretching? Good, because we're almost ready for our cheer. Are there any questions on A? I'm not going to continue. I think you can populate this, and that's now the remaining 49 entries in A and the remaining 14 entries in B, relative to those system equations. What's C look like? If you like just playing tic-tac-toe, you're going to love this, right? You can just build these grids. It's a little different than tic-tac-toe, but now it's 3 by 7. Maybe it makes for an interesting tic-tac-toe game. What is populated in C? We can build this one up. What's in the first row? 1, right? What about D? It didn't have any U's, direct feed-throughs into Y. The second row of C, what was Y sub 2 equal to? It was X3. And Y sub 3 was X5. And we didn't have any inputs directly coupled into our output. The D matrix was all 0. Questions on that? And if somebody asked for or had a different output configuration, maybe they were measuring velocities, then we would have had something here, here, and here, wouldn't we? I'm not going to put those in case you go and look at the notes and you go, what are those tick marks doing there? What was our first cheer? We could obtain our transfer function for the system as C, Si minus A inverse B plus D. Based on what we just derived, you could now plug in those 3 by 7, 7 by 7 7 by 2 and 3 by 2 matrices to get a transfer function for your system that would relate the 2 inputs to the 3 outputs. Let's now look at block diagram algebra by just looking at, maybe we have that G of S setting here, and we have an output, and maybe around that output we have another transfer function that filters that output and compares it to our reference input to create an error signal. And this is a classical block diagram. It's a feedback interconnected system where we have maybe our system G and feedback or a controller or compensator H. And we want to know what's the closed loop transfer function between R and Y in terms of G and H. Our closed loop transfer function, T of S, is now the ratio of our output to the input, Y over R. And it's not just G. It's some interconnected expression involving G and H to find T. What was one strategy that I had mentioned that might be helpful in deriving relationships for block diagrams or doing block diagram algebra? We're now just trying to find expressions that connect signals and systems in a block diagram interconnected way. Do you remember what I had suggested might be helpful? The output of the summing junction. Start writing equations for that, or seeing what you can do relative to E in terms of equations. E, in this case, is the output. What makes up E? Well, R does, and then minus what's coming in from the bottom. And what's coming in from the bottom? It's a signal that's made up of H filtering Y. E, the output of our summing junction, is then R of S, a signal, minus H of S, Y of S. If we want a transfer function, T, between the input R and the output Y, we don't want E's eventually in our expression. We just want R's and Y's. But we can also express Y in terms of E. Y is just G times that E, just by looking at this block diagram and how these signals and systems are interrelated. Now can write down that Y is G of S, E of S. And if I want to get rid of E's, then why don't I do some algebra and just substitute the first E expression or equation that only contains R's and Y's into where E is in this equation. Now I have Y of S is G of S times E, which is R of S minus H of S, Y of S. If I distribute that G through this expression, I now have G of S, R of S, minus G of S, H of S, Y of S. And that all equals Y of S. We called this algebra for a reason. Let's now collect like terms on the different sides of our equation. I now have Y of S plus g of s, h of s, y of s is equal to g of s, r of s. So far, I haven't had to make any kind of assumption on what these y's and r's and e's were in terms of signals. Were they vectors or were they scalar signals? Let's assume right now that we just have one input, r of s is a scalar, and one output, y of s is a scalar. Assume single input and single output. That allows me now to, one, just say that y of s I can factor out by having a 1 as a placeholder or as a scalar. In general, if this was multi-input or multi-output, that 1 would be an identity matrix to factor out the y. And this is now on the right, g of s, r of s. And since the left-hand coefficient, that expression scaling the output signal y of s, the Laplace transform of the output, is scalar, I can divide through. That's just some polynomial expression in s. I can divide that on both sides, and I now have y of s is equal to g of s over 1 plus g of s h of s times r of s. And if I wanted to, I could divide both sides by r of s to explicitly show that that block is our closed-loop transfer function. That's t of s. That's the closed-loop transfer function between the input r and the output y. In picture form, we've now collapsed that interconnected feedback structure into one block. And now what's t of s? That's our second cheer. T of s is g over 1 plus gh. So if I say give me a g, give me an h, give me a g over 1 plus gh, there's our second cheer. Go team. Do you see what I'm trying to do? Now, if you have a complicated block diagram, and in this case it's not that involved, we have some system, let's say it's g of s, and we have some kind of either filter or dynamics or controller in the feedback path that filters the output. So we measure the output, we filter it with h, we compare that signal to the reference signal. Those generate an error signal, and that error signal drives our system, and that just keeps going and going. It's in a closed loop configuration. And we can now collapse this, all of this, into our cheer. That's all t of s. We've now collapsed all of that into one transfer function, which is e over 1 plus gh, which is t of s. You derived it, which means that if you have this structure in front of you and you want to simplify things, you could do the simplification by implementing cheer number 2 and doing g over 1 plus gh, and then solving that. You now have a ratio of ratios, but you can simplify that to obtain a rational transfer function in terms of s with zeros and poles. And we'll pick up at that point on Wednesday. No class on Monday.